So good afternoon, everyone. Can I start, or are we waiting for someone else to come? I don't think so. Okay, my name is Tomasz Niedzielski. I serve as a professor of Earth Sciences at the University of Wrocław. University of Wrocław is the other university in Wrocław, the main university, where we have the Earth Sciences Department and Sciences Environmental Management. And I focus on hydrology and hydroinformatics. And today I'll be talking about satellite altimetry. The idea behind the entire talk is, or the introduction to the talk is, my story with altimetry, which dates back to, I would say, 2004, nearly 20 years, when I started my PhD student at Space Research Center in Warsaw. And at that time, when I was working in ocean altimetry, we're talking with my supervisor whether we can measure shelf seas or we can measure rivers. And at that time, we said, no, we know about a few papers which are doing this, but at that time, it's a little bit too risky to measure even medium or shallow rivers. 20 years passed, and today we are able to measure even narrow rivers. And with my colleague Michał, who will be giving the course after me, we are able to measure the other river, the one which is passing Wrocław, quite accurately. And this is the outline of the talk, which is in fact a little bit my story. 20 years back, oceans, and oceans today as well. But today we are able to measure water levels of medium or even narrow rivers. So the objective of the talk is in fact the history of satellite altimetry, which we can divide into 3 points. The first one, when satellite altimetry was not good enough to meet requirements of oceanography. So there was time in history of altimetry when it wasn't good enough to measure even oceans. So it's point 1. Then something very important occurred. And in 1992, Topex Poseidon satellite was launched. And it was very important for the oceanographic community to simply provide them with good data to measure water level. And then in 2012, I think, Michał, I think it's a good date, Cryosat-2 is the first altimetric satellite to measure rivers. So my talk will be the story on altimetry starting from oceans when it wasn't good enough. From through oceans where the altimetry was good enough to measure ocean water level, to hydrology to measure water level of rivers. So this is the outline and the idea of my talk today. And of course, we have to go back to history. And before altimetry, there were tide gauges. And as you see here, at low tide and at high tide, you can see the tide gauge here, and the water level is moving, and we can easily measure water level by the meter here. Sorry. The problem is relative observations. When the land is moving, for example, Scandinavia, it's not good for us because we can measure water level along with moving land. So, for example, when you have something which is moving up, this is land, and this is ocean, and ocean is moving up, and land is moving up, we have no water level change. So this is nice, but the tide gauge is attached to land. Not good enough for us today. So it doesn't mean it's a bad measurement, but unfortunately it's relative observation. So when the land is moving, the ocean is moving, okay. Of course, we have a water level rise, ocean level rise. Okay, 0. It's not good for us, but it's good for long-term records. Tide gauges are very old, so we are able to measure oceans since a few hundreds years back. Okay, but when we move a little bit farther, how we can improve it? We can find a different reference. So not land itself is a reference, because you know this exercise presented us that sometimes relative observations are not good enough, but maybe the orbit is our reference. And the idea behind altimetry is keeping the reference as orbit, keeping orbit as a reference for our measurements. And this very nice sketch, very nice picture, shows the satellite transferring signal to the ocean, and the signal, radar signal, is being reflected to the satellite, and satellite receives it, and we can measure the range. And due to quite complex, but not very much calculations, knowing the orbit itself, we are able to measure water level of the ocean. Of course, in respect to, for example, ellipsoid or geoid, to different reference figures we know in the Earth. So this approach gives us absolute observations, not relative as before, but absolute observations. Now, when we fly over Scandinavia, we do not care so much about land movements because our reference is orbit itself. So this is a great change in thinking of measuring water level, moving the reference from land to the space. Okay. In fact, what is measured? I said range. Range is the distance from satellite to water. So that signal travels from the satellite to water. It's reflected and goes back to the satellite, to the orbit. But of course, it's not that easy. I'm presenting the figure after Libusk and others, 2020, where you have the all complexity of what can be measured, or in fact, what can be, how we can present our water levels in respect to known surfaces. And as I said, we have ellipsoid, which we know. Ellipsoid is very famous for measuring usually coordinates, not heights, but heights as well, as you see. We have geoid here, which is the equipotential surface, and we have mean sea level and instantaneous sea level. So we have a few references around the Earth itself to which our range is calculated. So when we talk about products of altimetry, we do not talk about range. Of course, range is the most important thing, but we talk about products which are calculated out of range itself. Okay, so the other figure, which is a little bit more ordered, presents you key variables which you can meet in literature. So probably the most famous one is SLA, sea level anomaly, which is sea level change in respect to mean sea surface. It's usually 20 years mean or whatever. When you want to calculate the sea level to ellipsoid, you can meet SSH in the literature, which is sea surface height. You can also have ADT, which is absolute dynamic topography, the same referred to geoid. And finally, MDT, mean surface. So it's not the measurement, but the relation between mean surface to geoid, and MSS, reference to ellipsoid to mean sea surface. So these 5 abbreviations, 5 variables, are, you can easily find them in different data centers which serve altimetric data. Okay, but when you meet this data and when you download this data, they usually go through quite complex processing steps. And in this slide, I presented you a few corrections which are key corrections: ionospheric, tropospheric corrections, tidal corrections, as you saw a few minutes back, low tide and high tide. These variations are obvious, very well modeled using deterministic models, and this can be easily removed from the measured signal by satellite. And finally, waves. Sometimes waves are large. This can be removed as well. And inverted barometer effect, which is the effect of pushing low atmospheric heights and or low atmospheric low into the water. So water is pushing up and down in connection to how atmosphere acts. Okay, and now I'm still at the beginning of my talk. I'm talking about very basic things about conventional satellite altimetry now. So we think about oceans probably only. Why? Because when you have a satellite on the orbit and looking on the ground, so the radar signal is meeting the ground somewhere, and this somewhere on the Earth, on the ocean, and this diameter is large. 16 kilometers. Here in this figure, extracted from ESA altimetry, 16 kilometers is large. So imagine such a signal putting into Wrocław, so we have the entire Wrocław covered by one pulse. Oh, it's not nice. So imagine Odra itself, which is flowing through through the city. So it's a tiny point we can measure. It's impossible. That was the history and the basics of altimetry. 16 kilometers, the swath in English. Swath of the radar is too large to measure something on land. Of course, we can measure oceans with problems as well. And this conventional satellite altimetry is characterized by, is defined by orbit itself, by physics, by the geometry of the orbit. So when the satellite flies over the Earth, it's on some orbit which is configured, and it forces some spacing and repeat cycle. So these ground tracks are with some distance to each other, and the cycle, which is the time when the satellite is over the same ground track. After moving around there at the Earth, finally the same track is repeated after a given number of days. For example, for Topex Poseidon, it was 10 days. For Sentinel, it's 27 days. So it changes and it reflects the orbit. So this is how it looks, how the satellite, how the altimetric satellites sees the Earth. And now I'm beginning the first part of my talk. In fact, just look at the time. I think it's fine. Before Topex Poseidon. So we go quickly through satellites which were first altimetric satellites, but they did not meet the key requirement. In fact, the key requirement for oceanography is 10 centimeters. This slide taken from ESA altimetry as well presents you some names of satellites and this red line. This red line is a very important line in the literature. It's a 10 centimeters go at that time in 70s, 80s, I would say. And what it means? It means that oceanographic community wanted to have 10 centimeters accuracy, which for them will be a good level, a pretty good level to carry out studies in oceanography. This is the requirement the satellite altimetry had to meet over time to satisfy oceanographic community. 10 centimeters goal. Okay, look at this goal from the perspective of the map. This is satellite sea level anomaly map from Topex Poseidon, 2013, true map of how ocean looked at that time. And as you see here, the variation during one day, this is MJD, it's a Julian date, 56382, which corresponds to 31st of March 2013, and over the same day, one day, the amplitude in space in the entire Earth changes from -40 to 40 centimeters over the long-term mean sea level. So you see that 10 centimeters requirement makes sense, because over one day, the ocean over the entire Earth changes, standard day, I would say, over 80 centimeters. Okay, but look at the same problem from a different perspective. Not the perspective of space, but look at it from the perspective of time. This is one of the grids, so I don't remember which one. So you can simply select one raster here and look at this place in the Earth from the perspective of time. So you consider now a time series. And sea level anomaly, it's a figure, it's a navy or blue sketch, and using the red curve, I present the deterministic model consisted of a few main harmonics. And you see here that the red, it's a regular signal, a regular part of this variability. And this regular part changes from, I would say, with a linear trend as well, from -7, 8 to 0. So over time, we have at the same place the variability of about 8 centimeters, which is the regular one. But when you get rid of this regular signal, it's even bigger. So 10 centimeters requirement is really needed because if you have the accuracy of 40 centimeters and we measure 8 centimeters, it doesn't make sense. That's why the community asked for 10 centimeters. And now I explain it from the perspective of space and from the perspective of time. Good. Accuracies now. I still have time. Pre-Topex satellites. So these satellites which did not meet the 10 centimeters requirements. So GEOS 3, some dates for you, 75, 78, 1 meter. Not enough to measure what I presented now. The next one, 78, 50, 60 centimeters accuracy of sea level. Still not, so the error of the measurement was large in respect of what we should measure and what the variability of the ocean signal is. Now GeoSat 8590, 30-40 centimeters, and some ERS-1 and ERS-2 satellites, 25 centimeters accuracy, 291, 2000 and 1995, 2011. Still better, but not good enough to measure oceans. So these accuracies did not meet the 10 centimeters expectations. So what about hydrology? We think about oceans only, but the question is, what about hydrology at that time? So it's worth presenting some key papers. GeoSat applied in the Amazon River, a very famous paper in 1993. But look at these errors. I won't be reading it, but the text in bold. The level of accuracy may not be useful for routine hydrological measurements. 1993. And we have some measurements from GeoSat. We know it's not perfect for oceanography. People tried to work on rivers. Of course, Amazon River, which is large. We did not think about other river at that time. But it's not good for routine measurements. So there were attempts. You see papers, but they are not good enough to measure Amazon River, which is large. And the same with coastal seas. as well. The problem at that time, okay, we can look at coastal seas, but due to the contamination of the signal, a large swath I presented, transferring the signal into the land and into the ocean, so water, land, it mixes, it makes problems, and it's not good enough for routine hydrological measurements. Okay. And now the second part of my talk, Topex Poseidon and next satellites, because the Topex Poseidon it was a breakthrough in altimetry. So I'm citing a very important, I think the most important paper of today, Fu and others, 1994, just after launching the Topex Poseidon satellite. And it says that the accuracies were of 4-5 centimeters, beating the 10 centimeters requirement known in oceanography or expected by oceanographers. So this paper is one of first seminal papers showing that Topex Poseidon did this job, and we are able to measure oceans and provide data which are as good as the community wants. Launched in 1992, and a few years later, 1994, we see papers that show we have very good data out of this satellite. And why it's so important? Because we have climate change, and we like trends, and we are able to look at trends from the spatial perspective. Look at this map. This map presents you the rate of sea level change. This is famous in media, how many millimeters or centimeters the ocean rises every year. Okay, so on average is 3 point something centimeters, depending on which method of fitting the linear model you use. But it's not the same figure for the entire Earth. It varies spatially so much. So satellite altimetry was the first technique to allow these trends to be spread spatially. So you see here that there are areas where these trends are large, 2 centimeters per year, or where these trends are negative. When you take the average, you have something which is around 3 millimeters per year. So this is Topex Poseidon which allowed this analysis, but it's not the most important thing. Probably the most important thing which we were able to do with altimetry, and specifically with Topex Poseidon and its successors, was El Nino, or the entire oscillation, which is called ENSO, El Nino, Southern Oscillation. From Topex Poseidon onward, so meeting 10 centimeters requirement, we were able to monitor El Nino in sea level. This map, sorry about Polish language, this map presents you the El Nino 1997 in November, listopad, it's November. So the growing El Nino, one of the largest El Nino on records over the last 40 years. And El Nino is associated always with moving the water from Western Pacific to Eastern Pacific. Of course, warm water, disturbing fishery, and there are many environmental impacts. And we see here very precisely that this water here moved up over 40 centimeters. Having 10 centimeters requirement provided by Topex Poseidon, we are able to measure it. And what's the relation with hydrology? It's a large relation, because knowing this, we are able to predict it better, and we are able to predict impacts on hydrology in different parts of the world. I even published a paper that it has relationships between Pacific and Polish hydrology here in Odra River, and so on and so forth. So it's very important, even when you look at the map, which, looking at it, have nothing in common with Poland. It has, but it's because the altimetry did this job and measured that. Okay. And now we have Topex Poseidon, 1992. We know it's very accurate over oceans, and it met the requirements of society. But what about hydrology? What about rivers? This is a good paper by Birkett, 1998. So Topex Poseidon was 6 years on the orbit. And this paper says that we are able to measure water levels over large rivers. It's over 1 kilometer in width. Okay, it's large, but it's a very important paper. It says we are able, with the RMS error of 11 centimeters, we can do it. Okay, 1998. So it's a really, really nice paper showing it's doable. But of course, it has nothing in common with measuring or modeling continental rivers like our Polish rivers here with satellite altimetry. It's for large river. Okay, but it's still something. Okay, the next paper, it's by Beckett and others, 2000, I don't remember this, 2000 something. Of course, there are some limitations. Over rock terrain, we have problems with measurements over rivers. Okay, so we have nice technique, but we are working on large rivers, but still with problems in rugged terrain because of the vicinity of river banks. Okay, we'll move further. What about medium and small rivers? We talk about Amazon, which is pretty large, but what about smaller rivers? Okay, there were papers, and I cite very important sentences from them. Due to the size of the I will read it, of the footprint, which is larger than water bodies of small to medium rivers with 40 to 800 meters, the surrounding topography often contaminates the returned radar signal. This is what I started my talk with. Okay, 16 kilometers. So I'm sending the signal to the Earth. I've got a large swath of 16 kilometers, and this signal pushes the land, pushes water, and this produces some kind of contamination, they say, inconsistency. And in producing water level data, researchers carry out the analysis of waveforms. Waveforms are simply the graphs which show you, which represent the reflection of the signal from different bodies, water body from land. And it's very important to model what's water, what is not water. It's not the easy problem, but it's identified in that paper. So 40 to 800 meters rivers, okay, it's maybe doable, but the contamination is large. But it will not solve the problem of medium to small rivers. We have 16 kilometers wide swath, and we are pushing this signal, sending this signal to the land where the river is narrow, so the contamination is probably larger than the signal itself. So it will not solve the problem. Okay, from Cryosat 2 onwards, something happened over these 20 years to solve the problem of this contamination. And this is called SAR, synthetic aperture radar altimetry. The altimetry is looking into a land or ocean, into the Earth, from different perspectives. So it's not only looking using the nadir view, like the conventional altimetry, but it's looking along the orbit from different angles, from different perspectives. And this gives you the possibility of narrowing the swath 16 kilometers, okay, in one direction, but the other one is reduced to 300 meters, the number which is quite nice in between what we say medium to small rivers, 40 to 800 meters, okay? So this changes a lot. they simply employed, or we employed, the community employed the SAR radars on board satellite, making this swath different in the geometric properties. It's you see, it's not the circle itself. It's more like a rectangle here, not the full rectangle, but it's similar too. And it's one of these sides it's small, 300 meters. So this changes a lot, and this allows us the possibility to move altimetry into land. Okay, Sentinel-3A, you probably know it very much in Africa, and you see what SAR altimetry can do. On the y-axis, you see altimetric water level, so the water level measured by satellite altimetry, and in situ water level. You see a very nice agreement between the two. And talking about this paper, it's very important to say about the purpose. For example, in the countries like Poland, we have hundreds of in situ stations over the entire country. They are maintained by this Water Institute for Meteorology Water Management. They are automatic, they are well equipped, there is service. If something happens, they come, they replace things, and it's working operationally. But in the African countries, it's not like that. Sometimes you have 1, 2, 3 in situ gauges. The satellite altimetry, if it measures rivers which are small to medium, opens completely new perspective and fills the gap of distributing or mounting in situ gauges, which are extremely expensive in acquiring and expensive in maintaining in the field. So it changes a lot, and you see here with SAR altimetry it works well. Okay, so how to get this data? Because I said about waveforms, it's not easy, contamination, so it sounds tough, but it's not tough. There are centers, data centers, where you can download data which are prepared. One of them is HydroWeb database, where you can click, see, and probably register. Michał, am I right? I have to register, click, see, and you've got a really nice web map service, and you have this data calculated and provided for you. So it's excellent, and you don't need to worry about the corrections I mentioned before. They are theoretical corrections, they need to be applied, but these data are provided for the community. The other one is Dahiti Database Center, based in Munich, where the team of Christian Schwadke, with whom we cooperate. And you see here the pins over the earth where they measure water levels. So it's really excellent, and it's really changing things in hydrology, I think. So it's definitely the second database and the first one. They are ready for you to use without getting too much into how this data should be corrected, how these waveforms should be modeled. No, they are here available for the public, for the scientific community. Okay, and just look at the time. Okay, I have 20 minutes. So this was the introduction, 40 minutes introduction. And now say a few words on what we do here in Wrocław. It will be associated or connected to the other river, or to Polish rivers, because we are here and they are very good examples. They are medium, from small to medium rivers. And I'll be talking about two papers with Michał as well, in which we solved, I think, a few problems, or provided the community with the information how good these data are in fact. So the first paper published last year in Journal of Hydrology, it discusses the accuracy of the Sentinel-3A SAR altimetry over Polish rivers. So firstly, we wanted to check what the accuracy is. and it gives you, in a moment, it will give you a lot to be think over later. And then we studied the factors, environmental factors, which may play some role in controlling this accuracy. So what makes the accuracy bad or average, I would say. Okay, so I'll move forward. And this slide shows you in our country with ground trucks, the gray ones, so the trajectories or the paths of the roads of the satellite on the Earth, of course. And this ground trucks pass rivers somewhere. For example, when you have this place here, the ground truck is a satellite is passing over the Vistula River, the main Polish river, and such a place is called in altimetry virtual site. This is virtual site. So not the in situ site when you have all the expensive equipment, but you don't see anything there. But there is a virtual site for this satellite to measure water levels, a virtual station. Okay, and we measured over this available at that time, 2-3 years ago, we measured water levels having their neighbors. So every virtual site had neighbors presented in green here. Neighbors are true in situ stations, sites, water level gauges, which are located close to virtual sites to have some reference. Okay, so it's pretty easy, nothing very complicated, but we wanted to see how good altimetry, how well altimetry performs at these sites. And this map shows this. In hydrology, probably you know, there is a very famous statistics known Nash-Sutcliffe efficiency, which is a very nice measure, having its values from -infinity to 1, where something over 0.5 to 1 corresponds to good performance of the model or good performance of some measurement, for example, technique. And these circles, which are green here, or yellow, are, or even orange a little bit worse, are virtual sites where measurement agrees with data well. Okay, so it's, as you see here, it's a quite big set of sites over Poland where the agreement is good. Of course, don't look too much into detail because the circles are divided into comparison between downstream and upstream site. It's not that important for now. The important is color. Green, from orange to green circles, the collection or the set of them is large, is big. So we were happy with it. When you look at the time series and compare water levels collected at in situ gauges with water levels measured by the satellite, it's pretty good as well. Firstly, it's a figure C here, a river with 475 meters, something in between what the interval I mentioned. You see here a very, very nice agreement, but look at that, still 14.92 centimeters error, 15 centimeters error, given a very nice accuracy. So I'm happy with the figure. The agreement is really nice. It fits in phase, but it's still 15 centimeters RMSE. Okay. Then the next example, 480 meters and the RMSE of 37 centimeters. But it happens in altimetry. It's nothing. There is no error in it. Such cases may occur. Move further. Narrow rivers, the one which is in the top, 40 meters and accuracy 25 centimeters, and 70 meters in the bottom, 14 centimeters error. So you see here the agreement is nice, but the error is still between 15 to 30 something centimeters. Okay, so I would say. Okay, we thought about what is causing this error. So we were seeking whether there are some drivers which cause it. The most simple guess would be the land cover, because the contamination, all the signal, unfortunately not. You see this virtual stations, every row is a virtual stations, ordered in a descending order according to Nash-Sutcliffe efficiency. So 0.98 is the best performing station, minus 329 it's the worst performing station. And there is no nice or visible dependency in these colors which would allow us to see or to evaluate, to even hypothesize whether there is some agreement between type of land cover and the performance of altimetry of a Polish rivers. That was not easy, but we managed to identify something. I will not go through all this through this table in a great detail, but I will only let you look at the last row, which is the percent of virtual sites, virtual stations, so places where the satellite crosses the river, with complex river channel morphology. So when the river has sandbars, and these sandbars are close to the surface and this produces some kind of contamination. Or unfavorable geographical setting. For example, river is bending like Meandering River, and over these meanders there is a cross of our ground track. So not favorable geographical setting, and this, as you see here in these percentages of very good Nash-Sutcliffe efficiency, so very good sites, and a little bit worse sites, you see that there is a considerable difference between the two figures, and probably this bottom topography, so complex river channel morphology, you see the river bottom submerged forms close to the surface, or visible, and unfavorable or river settings may play a role. So to summarize, for Polish rivers, which are from 40 to 610 meters in width, of course, in our study, so this our studied sites, root mean square error was of 0.22 meters, 22 centimeters on average. So it's not that good. When you have a automatic water level gauge, you measure with centimeter accuracy, and we have 22 centimeters. When we compare these studies with other studies, we did it in the paper, it's very similar to what's presented in other countries. So this is pretty much state of art of the technology at the moment, and it's quite difficult to identify whether the width or the land cover had some impact. But as I said, the submerged bed forms or unfavorable river topography may have some roles in making the data more contaminated. Okay, but having this in mind, we thought about improvements, potential improvements. So 22 centimeters was not good enough for us to be satisfied. So we thought whether there is some geometric or physical signal to be interpreted and corrected. And we noticed that we are able to focus on slope of the river due to satellite ground shift, because the satellite ground track is not perfect, it's moving 1 kilometer left, right from the virtual site, and maybe this will have some impact on the accuracy of the measurements. And we tried to propose a method which corrects altimetric measurements and reduces the error of 22 centimeters. Of course, for our area, it was 22 centimeters, but as I said, the order the results from different countries were of the same order of magnitude. Good. So I'll finish my talk with these slides, where you will understand how it's measured. Normally, you have a virtual site over here, and virtual station, and these dots, yellow dots, are pings of the radar. So sometimes it's here. Every 27 days it matters. So next 27 days, okay, I'm over this site and I'm passing here. Then 27 days I'm passing here maybe. Oh, then I'm passing here. Every pulse, every radar pulse over this area is for standard 3 27 days. So as you see here, it's not stationary. It's moving. It's about as you see here, the scale is about 1 kilometer, I would say, left and right from the ground. But the measurement which is provided for a virtual station is provided for this site. Not for every site, for example, this one, or for that one, but it's provided for the virtual site which has fixed coordinates in databases. So together with our colleague in Munich, Christian Schwabke, we considered this effect. And when you look at the cross-section or maybe the profile of the river, it's very well seen. The virtual site is here with known precise coordinates, always the same. But the truth is, as you saw on the previous slide, the truth is it's not that case. The ground track is moving. Sometimes the measurement is here, sometimes it's here. So you see the offset, the altitude difference between the virtual site which is known, the coordinates of which are known, with a true measurement over the river. Okay, so we did the similar exercise. So you see here the ground tracks, and we considered the virtual sites and their in situ neighbors. Of course, we are happy in Poland. We've got quite a lot of in situ sites, so we're quite well equipped to carry out this research here. And we compared the two. The comparison shows that when we have a virtual in situ site here, the triangle, and then you've got the virtual site here, so the ground track crosses the river, and the true measurements are over there, over time, one pass, second pass, third pass, and so on and so forth. The agreement or the departure due to slope can change from moving down to moving up. You see the colors. So it's really a challenge. And when we presented this result on the map, it's very well visible. Look at that, how to read this map. I'll explain now. You see the decrease of the problem of the error from the left diagram here to the middle and to the third one to the right. So we were able to correct for slope, having this idea of non-stationary ground tracks in mind. So we corrected for them. Of course, using two approaches. I won't be going too much into detail, but it's doable. To summarize, we were able to improve by 25% the accuracy of altimetry over rivers, and now we can think not about 22 centimeters, but something around 15 centimeters as something which works for Poland. It's much better. When you meet something which is sub-decimeter, so about 10 centimeters and better, I think it'll be really usable. Of course, still worse than in situ gauges, but when you think of the countries when there is no in situ measurements spread well in the countries, these satellite altimetry, water inland altimetry is a perfect tool for many purposes, for water management, even for prediction. Look at that, 5 centimeters, almost 6 centimeters corrected, and we were able to provide the method which is fully satellite based. Of course, we work with in situ stations, but no, one of our approaches is satellite based, so it will work somewhere else as well. Before I finish my talk, I have to say that it's not the end. A few months ago, I don't remember when, the SWOT satellite has been launched. Of course, this paper is from 2014. It's a sketch of what was planned to do. But of course, it's a good idea. So we've got a satellite. Satellite is looking in another position, but it's looking right and left as well. So this is something extra on the top of SAR altimetry, which I explained in a moment. SWOT satellite has been launched, and it will provide definitely better data, I hope so, of a longer time period. And this is a chance for the community to have the altimetric satellite which meets the requirements of hydrology, so meeting the sub-decimeter accuracy for operational applications. So thank you very much for your attention. I'm very happy to answer the questions if there are any.